So start introducing myself first. I'm Kevin Anwar. Mm, This is my third year in teaching this course. So for my part, it's mostly sometimes it's hands-on. You need to do some things well. This is for water integration, gas integration. I'm not sure about the other two instructor, but for my part, I mostly really do optimization on material and guessing. I think previous instructor, Dr. Farid and Dr. Swan, we already covered the integration. Alright. Perun, I've been with Unimas since 2010 as a tutor. Then in the same year, go for my master's, finish in 2012. Then serving Unimas until 2018 before I go for my PhD at UTM, both of my masters and PhD is at UTM under the same center, Advanced Membranes Technology Center. But I finished my PhD about 3 years later. Then, yeah, been teaching this since 2024. Yes. Uh, so you can find the books is available. You can read it. Uh, the slide, video slide, and some graphic to help you understand. It's coming from the same slide, but it's shorter. But it's not covering all, but you get the gist of it. So for today class, divided it into 15 minutes, 15 minutes. Otherwise, it's very dry. I was told you because um, 7 of you should be. Aisha, I know, is doing my project, but others, Hubert, yes, I know. I'm not reply for the graduates, you know. How about you? Yeah, this. Are you guys okay? Not sure about the other instructor. Did they, you know, interactively? But for my class, normally it's, yeah, otherwise it's boring. But I do my best to get the, like, teach you guys all that I know. Like, that kind Alright. So we should start with some intro, but before we go for the intro, we ask you some question. So, yeah, just to see your understanding. The first thing to consider. Uh, So what is the first thing a factory does when the investment output reaches environmental limits? So, so what does they do? Mm, so normally, for those who just not sure about the other something detail cover this. So the first thing a factory does for those who don't have experience, they will say that yeah, we need to uh, prepare or boil the biggest what was it, wastewater treatment at the end of the line to treat everything. If there are 50 element in the wastewater, 50 compound, they will treat it all. So that question, I guess, you know, so for that question, yes, it can be done, but the cost will be astronomical, very expensive to treat everything. So that is what we call end of pipe treatment. Can be done, but very, very expensive. So in this class, what we're going to learn is we don't want to solve the end of pipe problem with the end of pipe solution. We try to find which process in the system that can be optimized. Yeah. So for this slide, it's based on book one. Okay, for book one, um, ellipse. So my um, research interest um, is mostly on the wastewater treatment, specifically dye, which let's see, heavy metal water, heavy metal rich wastewater, pit water as well, a lot of pit water, a lot of pit swamp in Sarawak, meaning a lot of water that has not been utilized. Yes, we have a lot of river, but one of the source of water is a pit. Uh, beside, so how do I treat it? Is uh, using membrane filtration, specifically ultrafiltration. So for the ultrafiltration, we don't just simply pass it. Yeah, we do the in-house membrane in the lab. So what we do, yes, we cast it ourselves, but we modify it with some additive, some particle to improve the Normally for ultrafiltration, it's just filter is the word. Beside ultrafiltration, I do photocatalysis. So for photocatalysis, what does it do? It can be used to uh, treat wastewater and also producing hydrogen. So it I say something you can get actually generate hydrogen using the photocatalysis. What does it? How does it compare with the electrolysis? Normally method used to produce hydrogen. Electrolysis, you need to use elec- electric electricity to do the water splitting. However, for the photocatalysis, you just need light. You just need light to activate the uh, catalysis. Hence the main photocatalysis or photo-activated catalysis. Catalyst. Okay. Okay. So Wan Alwi and Manan, this is two prominent professor from UTM. They are, let's say, a pioneer in water cascade analysis. There are several methods to do the water integration. You will learn it this afternoon. One of it is water cascade analysis, shortened as WCA. Yeah. So there are five type uh, water management hierarchy. So let me ask you. Wait, yeah, to make it interesting, let me do some poll. It's, hmm. Oh yes. Oh, yes. So the next question is, so which tier in the um, five five tier water management hierarchy is the most preferred for industrial resource efficiency? Is it fresh water or water elimination? So before we answer that, let me introduce each of it. So we start by asking, can the water demand be eliminated? So this is the level one elimination. So this is about water. Later we will cover about gas, which is it today or uh, the weeks. So can the water demand be eliminated? So for example, for elimination, we eliminate the water cooling, we change it to the air cooling. So this represent the theoretical ideal with zero operating expenditure for treatment, though it may require initial capital expenditure for equipment modification since you are changing from water to air cooling. So yes, of course, there's no water use now, just use air, but need to do some modification for the equipment to cater for the air cooling, like to do something to dissipate the heat. Level 2, which is reduction. So if it's not possible to eliminate, so another wise thing to do is to reduce. So this involve optimizing existing operation, such as fixing leak, improving the control logic. So meaning uh, one way to reduce the water usage is to reduce the water itself. So some might be leaking, and we could improve the control logic once uh, it's achieve certain temperature. We can reduce the amount of water used for the cooling. This typically this is the low hanging fruit. It's will be just a minimal capex, but with immediate smaller OPEX return. So do some changes to the equipment itself, do some modification with minimal capex, and at the end you can reduce the water usage or OPEX. Level 3 is the outsourcing. So for the direct reuse or outsourcing, this is our first step into process integration. So we take a source of effluent and send it to a sink, a process requirement without treatment. So in this case, the capital expenditure of it is limited to piping and pump. Yes, you need to do some modification since you need to reuse or outsourcing. Then the OPEX saving. The OPEX here referred to the use of fresh material. We don't want to use fresh material. We want to reduce it as low as possible because fresh water is expensive. So the OPEX saving are high, but because you reduce both freshwater purchase and the wastewater discharge fee. So meaning within the system, there's a effluent, we call it a source, and we direct it to a process that require the, let's say for the cooling. So we send it to a sink. So now you know two term, source and sink. Source is where we take it, water, where we outsource it, or then sink is where we direct the water. So for level 3 here, this is where it's interesting. We do what is water integration here. We do the optimization. Level 4 is or reuse or recycling. So here, level 4, we treat the water to reach required purity before reuse, but that water is still within the process. But we need to treat it. How to treat it later? There's a few methods to treat it, but yeah, of course, it's meaning you need to invest some capex for the new retrofitting for the new equipment. While this maximize recovery potential, yes, correct. Since we are using back the water, treat it, then send it back to the system. The OPEX and CAPEX of treatment unit often make this the last choice before the fresh water. The trade-off between regeneration costs and freshwater costs must be evaluated via the pinch. Yes, correct. Since this is, it seems like, yes, it's good to regenerate, to treat the water and then reuse it, but we need to see how much the cost compared to just buy the fresh water and use it. No need to regenerate. So if the system, once you do the comparison, you see, hey, regeneration is better. So by doing regeneration, we reduce the amount of wastewater or wastewater discharge fee, and you can reduce the amount of fresh water that you need to buy since you are reusing the water back. So back to the question, which tier in the 5 tier management hierarchy is the most preferred for industrial resource efficiency? So for this case, it's always, if possible, we go for the number 5, number 1. We want to reduce as much as possible or don't use any fresh water. Just change it to something else, but sometimes it's not possible. So the matter management hierarchy, championed by one Alvi and one is the North Star for industrial water conservation, but later you'll see some other name like Professor from Professor Fu, God, she don't know. It's Malaysia, yeah, but in private university, also doing water conservation like this. So the answer is for this question, uh, fuel elimination. If was why it's a top priority because it's remove the demand entirely, meaning there's no fresh water introduced into the system. As one Alwi and Manan highlight, we must question the necessity of the demand before we invest in optimizing its supply. We prepare the next issue. We do a point now. All right. Let's check. This is what I explained. This is frame number four, regeneration. This is level five. So next is the water footprint reduction. I send you the poll. It's asking according to the definition, what does the gray water footprint represent? Sure, sure. You know what, please? Let me explain first. That is water footprint. So, so how do we measure color? usual water income. So when we look at water consumption in industrial facility, we cannot just look at the water meter at the front gate to truly understand environmental impact. We need to track the product entire water trail, both the direct and the indirect trail. So this tracking of the product entire water trail is what we call water footprint. So to make this complex metric practical, water footprint are classified into a spectrum of three different colors. So we have green, blue, and gray. So green water footprint or soil moisture. So the volume of rainwater stored in the soil that is evaporated and transpire or evaporated by the vegetation. So how does it relevant to the industry? So it is highly relevant to bioenergy, agricultural raw material, or the forestry feedstock. So green water footprint or soil moisture is the volume of rainwater stored in the soil that is evaporated, transpire, or incorporated by the vegetation, the plant. Blue water footprint or direct extraction, it's a volume of fresh water drawn from surface water bodies like a river, lake, reservoir, and groundwater aquifers. So, in relation to industry, this is the physical water that, that they pump into the factory gate for process cooling, steam generation, and so washing. So green water is rainwater stored in the soil. Blue water is the fresh water that you drawn from the surface water bodies, including lake, river, reservoir, and also the groundwater aquifers on the ground. And the last one is the gray water footprint, or you can also call it the pollution indicator. So the gray water footprint is defined as the volume of fresh water required to assimilate and dilute the pollutant load such as chemical oxygen demand CO2 from a process back to standard ambient water quality standard. So for process, for process engineering in relation to industry, uh, this is the most critical color. So it doesn't represent the water that we physically use, but it's amount of natural water degraded when you release the waste. So you have the gray water released to the environment. It so that fresh water dilute the pollutant. So the amount of fresh water that dilute the pollutant that is, you know, gray water footprint. So how do we calculate the low water footprint? So return back to this. So based on the poll, the what does the grey water footprint represent? It represent the last one, number three. Volume of fresh water required to dilute pollutant to ambient standard. So it's not the amount of pollutant that we calculate, but the amount of fresh water that is being used to dilute the pollutant when it's being discharged from the factory, from the compound. So next is yeah. So how do we calculate the blue water footprint? So blue water footprint we are using chainsaw method. So why we need to use the chainsaw method? Because we want to trace the cumulative blue water footprint across the product entire process chain. So based on this equation, so we take the volume of fresh water that entering the process step or being consumed by the process, and we divide it with the total mass of the final product produced. Simple as that. How much what fresh water that is consumed by that process divided by the total mass of the final product. So the product is your product. The fresh water introduced into the process is to make that product. It's different compared to uh, gray water footprint. So the gray water footprint is calculated using the wastewater flow rate, which is true because it's directly related to the wastewater. And beside wastewater flow rate, it also can be calculated using, also being calculated using pollutant mass load. Uh, Indicator involved is something like COD, chemical oxygen demand, or TSS, total suspended solid. Those who work or intern or have experience in wastewater, they or water analysis, they know this term. The formula represent the waste load L divided by the difference between the maximum allowable water quality standard and the natural concentration of the pollutant in the receiving environment. So, of course, we cannot release the wastewater if it's more than the water quality standard. It's a no-no. So, in this equation, the first term there, sorry, the term C max is referring to the maximum allowable water quality standard. And C natural is the natural concentration of the pollutant in the receiving environment, meaning within that environment, it's there. Yeah, the compound is there. Table 20.2 refer to slide 12. So based on this table, what is it? 2022. So we have water footprint. We also have what else? Water pinch life cycle costing. I explain two first. Water footprint and the water pinch analysis. So the primary aim of water footprint or WF in short form, it evaluate quantitative water use and quantify pollution generation over a life cycle. The primary aim for the water pitch analysis is to integrate and optimize the direct matching of source and sink. So what is source is where you get the water and sink where you direct the water within the process to mathematically minimize the freshwater intake. So we do pinch analysis to minimize the water, freshwater going into the system. So that freshwater is referred back to the blue water footprint. And at the same time, we reduce the wastewater generation. This is water pinch analysis. So water footprint is the post-assessment tool, meaning it happened already. You do the post-assessment tool. For the water pinch is an active design or optimization tool. So before you do the system, yes, you can do the water pinch. During the system operate, yes, you can still do the water pinch. Even after the system. After it happened, yes, you can do the pinch analysis. So we can say the water footprint, it's act like a financial audit. So it tell you how much water you spend and polluted after the products. But for water pinch analysis, it's like this is economic point of view. It's like a wealth management plan. So it actively restructure your process network to ensure that you consume the thermodynamic minimum. Okay. Another question. See, so another question, imagine our factory successfully implement water recycling, cutting our fresh water intake from 100 of ton per hour to 90 ton per hour. But our wastewater treatment plant, COD is chemical oxygen demand, one of the unit or method to analyze water quality. But our wastewater treatment plant COD discharge concentration remain high. Which water footprint have we successfully reduced? Which one still need work? So the answer to this question, we have reduced the freshwater, meaning the blue water footprint or blue footprint by conserving con- the raw fresh water. But since the COD is high, remain high, but the gray water footprint remain high because our pollutant load is still degrading the receiving water body. So keep in mind that gray water is not about the pollutant, but how much fresh water needed to dilute the pollution. Okay. Second. Right. So next is the uh, concept of life cycle costing, since it's appear in table 22. How does it relate with the pinch analysis? Let me clear another point. Mhm. Okay. Put another point that explains this concept. So the acronym for life cycle costing is LCC. So in this case, it's a life cycle costing. Later, after a few slides later, you will see another LCC, but that one is limiting composite curve. It's not the same. This is a concept. LCC limiting composite curve is a method of optimization tool. This is a passive retrospective economic assessment tool. Limiting composite curve is the targeting like a water cascade analysis. It's okay. So life cycle costing versus water pinch analysis. So before we look at the graphic of water network, we need to address an acronym trap. So if you search LCC in industrial water management literature, you will find two completely different concepts. The first is the life cycle costing. Another one is, yes, the limiting composite curve. So LCC, this is LCC for this life cycle costing is developed by the US Department of Defense to calculate the absolute total cost of a product or system over its entire lifespan from conception to manufacturing. Daripada konsep, dia buat lagi until it's to manufacture the product. Through operation to disposal. So for concept manufacture using the equipment itself, then disposal of the equipment. So in water system, because this is for this topic, it's about water. It is a post assessment tool. It acts like a passive financial auditor. It is highly comprehensive, but it's require an enormous amount of historical life cycle data just to tell you what an existing design costs. So it cannot tell you how to optimize the network physical layout to safety the water, unlike the water pinch analysis. So this is where the water pinch analysis is in. So WPA is not a passive accounting tool. It's an active design, like we previously covered. It's an active design and it is an optimization tool. Instead of auditing costs after the fact, WPA look at the physical demand and supply of water in your plant or in the process and tell you that the absolute thermodynamic minimum of fresh water you need to buy and wastewater you need to discharge before you even design the piping. So before you do any retrofitting, that's why there's a pioneered by these two prominent professor Manan and Sharifah Wan Ali. Even in Unimas, yes, we do it. We have team from mechanical before any retrofitting. So when we do the feasibility study, they actually not mine. They actually calculate so how much freshwater, where do you get the freshwater, and how much the wastewater that you can reuse or recycle before you discharge it. It's possible to there's a software. So since we are discussing LCC, so we just introduce ourselves. So the second LCC, which is the limiting composite curve, is when we want to optimize the mass transfer dissipation. So you haven't heard this term yet, MTB, mass transfer dissipation. We have non-mass transfer dissipation, not yet. I haven't covered yet, but yes, after this, we want to optimize mass transfer dissipation. We plot them on a graph with the contaminant concentration C in ppm on the y-axis and the mass load of the contaminant x-axis. Those who learn it or from chemical engineering background, uh, I know, I think they know. Yes, they should know about the limiting composite curve. You learn it heat integration or heat and mass transfer. So every water using operation has a profile defined by its inlet concentration and the outlet concentration. And if we combine this individual profile within the concentration interval, we get a single continuous stepping line representing the system total absorption capacity, which is what we call a limiting composite curve. After this, we'll have a let's see, example, one of the purpose. Okay. So to find the minimum, we draw the water supply. Okay. So that water supply line, if it's crossing the curve, the composite curve, we call it a pinch point, similar to WCA. Okay. So return back to the poll question. So in the context of industrial resource conservation, what is the primary difference between life cycle costing and the water pinch analysis? So the answer is betul. It's a cost assessment tool that calculate total cost over an item, while the WPA or water pinch analysis is an in-process targeting and optimization tools. Okay, majority of you, not majority, all of you is excellent work. Yeah, all of you, majority of you choose C. So let's reinforce why this is the correct answer. Remember, life cycle costing is a retrospective cost assessment method. It operates like an audit. It requires huge amount of life cycle data to sum up capital and operating expenditure over time. It doesn't actively change your process design. However, the water pitch analysis, the WPA, is the in-process targeting and design tool. It allows you to calculate target for minimum water intake and maximum reuse. We even lay out our piping network. So WPA tell you to design the system. LCC, in this case, life cycle costing, is to evaluate the financial impact after the design concept are set. Okay. I hope it's clear. Have you learned how to pinch? Not yet. Yeah, not yet. But you know what is pinch now? How does it different with the water footprint and life cycle costing, the water minimization? See. This is an old paper, 1994. They are, I could say, a pioneer, like, for this method. In the end, this is the limiting composite curve. This is how we, like, this is what I told you, the water supply line and crossing the, so, oh, mathematically we call this tangent to the limiting composite curve. This point is what we call the pinch point, the optimized point. So this method introduced by Wang Smith in 1994 water minimization methodology. This is the a foundation to the water pinch analysis. After this, there's a lot of method, but it started with this methodology. So unlike the general water conservation hierarchy introduced by, let's go, Alvi, Wan Alvi and Manan, uh, the Wang and Smith method provide a rigorous, it's a graphical way to calculate the absolute minimum water target for mass transfer based operation. The paper is quite thick and, and using typewriter. So the core concept is three recovery pathway. And again, uh, this is for the mass transfer based approach. Let me introduce this mass transfer based approach. Okay, just like we go for the over. So what is a mass transfer based approach? So this operation use water as a lean solvent. So the water pick up contaminant, and these are governed by the purity constraint and the concentration guideline. This is a mass transfer base. There's a mass transfer occurs still. Another one is non-mass transfer base. So non-mass transfer base is a operation where water is lost. So meaning water going through the system, it lost. Either it's evaporate in the cooling water or become a steam injection. So in this operation, there are no mass transfer of this. Without any mass transfer that refers between two distinct references. We can say water come in, water no water goes out. As simple as that. But it's not that simple, yeah. But it's like that. Actually, the water is turning into another phase. Yes, a liquid enter into out as a liquid, as a steam. Alright. We can back to the foundation of uh, what the pinch analysis. Let me give this some yes, activities. But in final exam, the question is not like this. Just uh, it's not a ABC. For the final exam, we need to calculate, then justify the answer. Right. Tapi po satu, itu paling berat, but make it as easy to understand as possible. So the core concept, there are three recovering pathway for the water now, or wastewater, since this paper is based on wastewater. So in their groundbreaking 1994 paper by Wang and Smith, this duo established that if we exclude making fundamental changes to the process chemistry, there are three and only three suitable dynamic pathway to reduce the wastewater in the industrial plant. So the three is either direct reuse, regeneration reuse, or regeneration recycling. Only three. Hmm. If you don't want to make any fundamental changes to the operating the process chemistry, only three pathway possible to reduce the wastewater in the industrial plant. First one is the direct reuse, is taking the wastewater directly from an outlet, not necessarily at the end, any outlet within the process, and feeding it to the as an inlet to another process, not just for cooling or heating. It can actually mix it and become something. Another one is regeneration reuse. It's partially treating wastewater to remove contaminant before using it in a different process. Last one, the third one is the regeneration recycling. Regenerate the wastewater and recycling it back into the process where it has been previously been used. So what does these two, regeneration reuse and regeneration recycling, if you compare, what does it? What is the difference? So for regeneration reuse, you take that wastewater, you partially treated it, and you use it in a different process, but still within the plant, but different process. Eh, for regeneration recycling is you take the wastewater, you regenerate it, and you return it back to the same process that uh, using that water. So reuse and recycling is a different thing. Next is uh, the desalter. Look at the refinery unit, the desalter. So in this paper, Wang Smith is using desalter as the case study. So let's look at the classic refinery unit, the desalter. We mix crude oil with water to extract salt, and water acts as a sponge or the mass separating agent, picking up the salt. So if we plot this process on a graph with contaminant concentration C on the y-axis and the contaminant mass transfer on the x-axis, or if you refer to the paper, just a paper now. Okay, so M, the x-axis, we get a straight line representing the mass transfer. Now we have the design choice. Either we want to maximize our water reuse or the other thing. So if we want to maximize our water reuse potential, to do this, we must feed the desalter with water at the highest possible inlet concentration. We refer that as the C in max. C in max. Okay. C in next and let it exit the maximum possible after concentration as the C out next. Yeah. Banyak. Tidak. So this boundary line is our limiting water profile. It is a thermodynamic limit. It represents a bottleneck in any practical water supply line must be designed that we design must lie entirely below this limiting profile to ensure that you always driving force mass transfer to occur. So what if we have multiple water water using process in our plant? Normally there are multiple water using process in the plant. So we plot the limiting water profile of all operation on the same concentration versus the mass load graph. Yes. By combining this individual profile within the concentration interval, we construct the limiting composite curve. The LCC represent the plant capacity to absorb contaminant across different purity. Uh, okay, this is all the process. This is one, two, three, four. This is the limiting process data. Or if you have many multiple water using process, so so from the multiple water using process is table one, you can generate the limiting composite. So this is the limiting composite. Next is the we draw our fresh water supply line starting from the 0 ppm here. Since the slope of this line representing the reciprocal of the water flow rate f equal to delta m over delta c, maximizing the slope minimize the water flow rate. So we pivot the line until it just touches our LCC. LCC here refer to limiting composite curve. This is the tangent point of contact, or we call it the um, water pinch point. So in the let's see, 9 kan. So in this problem, uh, using fresh water for every process require 112.5 ton of water. So by constructing the LCC, in this case, we, and pivoting our supply line to the pinch point, we can target a minimum flow rate of only 90 ton per hour. A massive 20% reduction actively achieved purely through optimal reuse. Rehat tak? Ah, so for the poll question, according to Wang Smith technology, why must a physical water supply line lies below the process limiting water profile or limiting composite filter on the concentration versus mass load cover? The answer is B. Ataupun nombor dua. To ensure a positive concentration, the reinforced exists for the containing non-filters flow from the process stream into the water. So, because the mass transfer is driven by concentration difference, which is that one is rule of thumb. If your water supply line, this is why the answer is number two. If your water supply line process goes above the limiting water profile, the concentration of water would be higher than the process stream can tolerate. The driving force would go to zero or reverse, making it thermodynamically impossible for the water to absorb the contaminant. So by keeping the supply line below the LCC, it can guarantee a feasible design that respects the thermodynamic limit of the planet. Okay. That is the this is the foundation of water pitch analysis. Okay. Next is water integration and water pitch analysis. Explain this. Okay. 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 Mm, okay. Next is the water integration and water pinch analysis. So, looking at this slide, before we dive into the magnetic water pinch, we have to address how industry usually set water saving goals. Normally, the plant manager look at the last year water target and target a generic 5% reduction, and call it a thing. So this is what we call a apparent target. It based on the past data, there is no thermodynamic limits. So the water pinch analysis pioneered by the Wang and Smith, that's on the 1994 paper, completely flipped uh, this method. So WPA is a systematic technique that allows us to find the true minimum target instead of just focusing on the 5% reduction. The absolute thermodynamic limit of a freshwater plant needs before we even design the single run of piping. It tell you exactly how much water is theoretically possible to save, so we can make a massive step change leap in cost and resource conservation. So the core concept is to see that water as a sponge, as a mass separating agent. So we not just treat water as a utility, but we treat it as a mass separating agent, or MSA short. Think of water as a clean, lean stream acting as a physical sponge. So the job of water in this case is to enter the process, then to contact the contaminant-rich stream and absorb this impurity and exit as a dirty spent stream. So this is concept of water as a mass separating agent or sponge. Because we assume that the water flow rate entering that operation is equal to the flow rate of its leaving, so we can call this a fixed flow rate problem. The water entering is equal to the flow rate of water entering is equal to the flow rate of water exiting or leaving. So we call this a fixed flow rate problem. This include the classic mass transfer based operation like the vessel cleaning, yes, gas scrubbing, and solvent extraction. So the crucial philosophy is in process versus the end of pipe. So the golden rule of WPA, water pinch analysis, is do not solve an end of pipe problem with end of pipe solution, which I show you the first question before we start the class today. So what does it mean by do not solve or don't solve an end of pipe problem with end of pipe solution? So if that plant is discharging a highly polluted water, so your reflect as an engineer, it shouldn't to build an incredibly expensive wastewater treatment facility at the property boundary where you release it to the environment. Unless you have thoroughly explored the in-process solution, either you do the three method proposed by Wang and Smith uh, paper, either you do direct reuse, regeneration, or recycling. An end of pipe treatment plant is almost always the most expensive and it is the least efficient option. So the WPA, water pinch analysis, forces us to look inside the process boundary to find a reuse opportunity first. So WPA okay, work in a two-step, two-sequence step. First, we set the target, the water target, and second, we design the water network to meet those targets. So when we plot our water using process, we eventually hit the thermodynamic bottleneck where the driving force for mass transfer is at its absolute minimum. This bottleneck is the pinch point, like in heat integration, the pinch is the thermodynamic dividing line of your plant. And studying its location is the secret to unlocking the optimal cost-effective water reuse. So by doing the water pinch analysis in the process, we can identify which process, which piping, which line within the process that we can do the three, either direct reuse, regeneration reuse, or regeneration recycling. So the answer for the poll, wait. So what that Why does pinch analysis require setting fresh butter and roast butter target before designing the actual criteria? So the answer is to ensure we establish the true thermodynamic limit of the plant, preventing us from setting for minor apparent historical target. Oh, next is the mass pinch analysis. Mm, So there are five steps for mass pinch analysis. One, plan audit on mass network. Do data extraction, target minimum resource, design the minimum civil mass network, and economic analysis. Assessment. We go one by one. Mmm, lagi 4 menit dah. Cek. Mm, you break for 10 minutes. Same thing. So we continue. Mm. Step one. So so you, the core concept for step one is you cannot optimize what you have not made. So the plant audit involve inspecting the physical plant piping, meaning you go through the PFD, go through the PNID to construct the complete and rigorous water mass balance across the entire industrial site. So PFD is the process flow diagram, PNID is the piping and instrumentation diagram. So be so before we write any single equation or draw a single curve, so we must, you know, put the hard heads and walk across the plant floor. So step one is the plant audit. So we map every single water using unit to establish an exact water mass balance. We can categorize every operation into one or two operational archetype, either mass transfer based system or the non-mass transfer based. So the mass transfer based or MTB, so in this case, the water will act as a solvent or the mass separating agent, like the sponge that I explained before, to pick up the impurities. This is also called fixed flow rate operation. Another one is the non-mass transfer based NMTB. So the water is used as a utility or heating, cooling medium or reactant. Normally, we see this case in cooling tower, lower. So this is what we call a fixed contaminant, not operation. So for the step one, let me just okay. So this is for step one. So during a plant audit, you identify a gas scrubbing unit where water is sprayed to absorb sulfur dioxide from a flue gas stream. So how should this operation be classified? Is it a non-mass transfer base or the mass transfer base or what? Pure water disposal stream with zero mistake. You can answer this after this. So for step two, the data extraction. So once the mass network is audited, next is we extract the limiting water data. This means identifying every water sink or demand requiring water, every water sink. So water sinks refer to demand that require that water or the water source defined as the wastewater supply generated. So two terms, sink and source, and extracting their allowable flow rate and limiting concentration. So now that the plant is audited, we go to the step two now. So we don't just write down the existing flow rate. So if we only look at what the plant currently consume, we are setting an apparent target like before or the traditional way based on the past achievement. Instead, what we do is we extract the limiting data for every thing. We ask what is the absolute maximum concentration contaminant this equipment can tolerate before it corrode or fall or fail. Next is for every source, we determine the maximum outlet concentration. This limiting data establish our thermodynamic boundary. So meaning you have two, let's say a table. So within after the mass audit step one, we extract the data into two column. One is the water sink. Another one is the water demand. So question that we can ask is why is it critical to extract the limiting concentration, the C max, rather than simply recording the current operating condition concentration of the plant? For the first question, during the plant of the 25 the gas scrubbing unit, the water is sprayed to absorb the sulfur dioxide. Remember water as a sponge from a flue gas stream, how this question should be perspective is a mass transfer gas. No? Yeah. So this in this case, the water is a mass separating agent. No? Now let's go to step three, the setting minimum utility target. So this is the mathematical peak of this lecture. So before designing any piping network, we target the absolute minimum fresh water required and was water discharge. So this is done either using graphical like limiting logic curve or algebraically using the water cascade analysis. So how to explain? So the gist is we target before we design. So if you design a network of pipe first, what you do is just a guessing. So we target, then we do design. So in step three, we construct our water cascade table, WCT. We sort our concentration level, convert them to pretty fraction T, and calculate the purity difference or delta P. We cascade the cumulative pure water surplus through the interval. So if we assume freshwater intake, we will get a negative cumulative value. This is thermodynamically invisible. So meaning this cumulative value here, this has already been solved. But without this freshwater supply, actually the value for cumulative here is a negative. So we eliminate the largest negative deficit. So with among the many negative value here, we find the biggest, the largest negative deficit, and use that value as the baseline of how much fresh water we should add into the process or into the system to avoid the cumulative water surplus being negative. So the point where the cumulative surplus is exactly zero, in this case here, zero, this is our water pinch point, similar to the limiting composite curve. But for limiting composite curve, it's actually the tangent of water supply line to the SOC. Okay. So uh, in the water cascade table, so for question step two, why is it critical to extract limiting concentration CPAC rather than simply recording the current operating concentration of the plant? The answer is A. Yes. Limiting concentration allow us to define the maximum permissible contamination, opening up the maximum degree of freedom for water reuse. So if we only record current operating concentration, so we restrict ourselves to historical design. So by extracting the true physical limits of the when we unlock the maximum potential to reuse the spent water. The step four is is the water network design or retrofit on. So with the target established, the minimum freshwater target of 90.64 ton per hour for problem 8, we design the physical network of connection to achieve those targets using three core heuristics. So heuristic one is now we build the network in step 4 to achieve the target we just calculated. In step 3, we calculate the target. We must follow this three golden heuristic. Heuristic one is never cross the pinch. So meaning do not feed water source from above the pinch. Higher concentration meaning to sink below the pinch over concentration. Higher purity requirement. Doing so will violate the thermodynamic containment and inflate the freshwater demand. Heuristic number two is cleanest matches first. Start matching your cleanest source to your cleanest sink. This is, yeah, you should follow this. Heuristic number three is map source sequentially. Yes, cascade span water down to lower quality portion before introducing fresh utility water. Let's go back to the cascade analysis technique. Okay? So in this so so in step three, you see there are several method. I see. Yeah, yeah, three method. There are many more. You can refer to the code, but in this case, I will just highlight these three. So to achieve the thermodynamic rigor, we must move beyond the graph and into the water cascade analysis. So by choosing this second method, we this numerical tool eliminate the graphical inaccuracies by drawing the curve. So how to do it? You see, establish the purity intervals. So first, we arrange all limiting concentration inlet and outlet, either both, all of it, either going in or going out in the ascending order, regardless of inlet or outlet. So we arrange it in a ascending order like this. Then in each of the interval, we calculate the mass load using the M equal to F times delta C. If M is positive, the interval is a surplus. If negative, it is a deficit. Next, we sum all this load across interval. This represents the water capacity to absorb the contaminant. Identifying the true pinch in our first iteration, we may see negative water surplus, which I already explained. This is impossible. We cannot have a cumulative pure water surplus negative value. So you will find the highest value, then we use that value as the baseline for how much freshwater should be added into this process. With, So what about this tree? So for limiting composite curve, this is a plot of contaminant load versus the concentration, which is the same method introduced by Wang and Smith in 1994. So the strategic use of this LCC is to define the envelope of the process tolerance. Another curve type is the sourcing composite curve. So this is for comparison of available effluent quality versus the required process quality. So when to use is identify with internal reuse level 3 within the hierarchy. Replace the fresh water as compared to water cascade analysis. Mm, okay. So this method is based on Manan et al. 2004. So this is serve as the uh, it's equivalent to if you had water surplus diagram WSD. So by using water cascade analysis, it will reduce the trial and error graphical plotting of water curve to mathematically pinpoint your target and bottleneck instantly. Okay. So what is water cascading? Start with what is water cascading. So it's allow the pure higher purity wastewater source to directly satisfy the lower purity demand of sea. That's all. That is the water cascading going from high to low. So if a process produces 100 kg per second of wastewater at a high purity of 100 ppm, refer to this graph, refer to this illustration. The another process require 50 kg per second of water at lower purity of 200 ppm. You can directly cascade 50 kg of that wastewater to the sea. So this A here, 10.9A, this is without cascading. Yes. B, yes, you cascade. Instead of go straight to the wastewater, you introduce it to the next process. So since you introduce it and it meet the requirement of the purity level, so the amount of wastewater is reduced by 50. Yeah, 50 kg by 50%. And no fresh water needed for the second process. So by cascading, instead of discharging, you simultaneously reduce the plant freshwater intake by 50 kg per second, and it wastewater discharge by 50 kg per second. So this is the simplest illustration of water cascading. Okay. Okay. Start with the first column. So the first column is concentration CK here. And column two is the what the purity PK. So first, list all the concentration CK and PPM from your audited process. So remember, this is a step three. Step one is you do the mass audit. Step two, the extracting that into a sink and demand. Step three is do this water targeting. So list from audited process in sending order. Sending order means from lower to the highest. Convert this concentration into pretty mass fraction PK using the formula, this formula for pretty. Column three. So column one, column two, column three is the um, purity difference. It's okay. Column four and five. Okay, four and five is sum up all water demand sink and water supply source active at each purity level. So where do we get these two? From the step two, extracting the data, demand and source. Next column six is to net interval flow rate. So sig minus source minus demand. So D here, FD is for demand or equal to sig, and S here refer to source or supply. Okay. So net interval flow rate here refer to demand plus yeah, source. So like this, minus 1.2 plus 0.8, negative 0.4, and so on. Column 7, cumulative flow rate FC to split your baseline cascade the net flow rate down the interval starting with an assumed freshwater flow rate of 0. So when you start this table, it should be start with 0, the FW equal to 0. The final value at the bottom of this column represent your baseline water discharge. So this is FWW is referred to wastewater flow rate, FW freshwater flow rate. Right. So once the flow rate are cascaded, it's cascaded for this 2.06 times 0.4. Interesting. Okay. So how you do the cascading? So 2.06 minus 0.4, you get 1.66, 1.66 minus 0. Negative 5.8, 1.66 minus 5.8, you get negative 4.14 plus 5, and so on until you get the FWW. No? The column 8, pure water surplus, is defined. Oh, that's it. Okay, so okay. Pure water surplus or deficit is defined as FC multiply with P. FC multiply with P. Oh, delta P, sorry. Delta P tengah-tengah. In between PK, because if you follow this line, there is no number in between. So what you need to do is schedule minus this multiply with FC. Next is the column 9, the last one is the cumulative water surplus. Here we do the cascading as well. Oh, what is cascading? You multiply, oh no, sorry. You subtract it or add it. Like this one zero plus this, from this minus this, from zero plus this, and so on. Since you are starting with zero first, I can guarantee you you will get a negative value in the cumulative water surplus. Mm. Hmm, for number apa? Yang tujuh. In a water cascade table, what does a collective pure water surplus of exactly zero indicate? Yes, exactly. Yes, it's indicated water pH point where the mass transfer driving force are at their minimum. So ada 20 minit, 25 minit. Like any question, you just ask in the question on the chat. That as well. See. Okay. So once we identify the target from the water cascade analysis from the LCC or the sink source compositor, so like okay. So we have done the plant audit. We have extracted the data. We have done the WCA to target to find the targets. So now we have a pile of numbers, yes, but zero pipe, no retrofitting on it would be done yet. So step four is where we actually build the network. Mm, today, as the system engineers, we are going to connect our wastewater source to our processing using the golden heuristic that make our network thermodynamically foolproof. Um, So, so step four begin with the boundary line. We take the pinch concentration we calculate in step three. Example, the 700 ppm pinch in problem 8. Draw the line. So this line, so below the pinch is the clean zone where the concentration are low and purity demand are high. Above the pinch, yeah, the dirty zone where concentration are high. So this is where the heuristic come from. Okay. So the golden rule of water node design is to ensure that we do not waste the purity potential of water stream. So below is clean, above this red line is dirty water. So, so the first golden heuristic is do not cross the pitch. So meaning the water source with the concentration higher than the pinch to a sink with the concentration lower than the pinch. This is the cardinal sins of messaging, meaning water here cannot pass through this pinch and vice versa. Next, the second golden heuristic is prioritize low concentration sink. So reserve your highest quality water or fresh water for the sink that has the strictest purity constraint. Next, the third one is a match high with high. So match source with high contaminant level to sink that can tolerate high contaminant level to maximize the driving force. Sembilan Mei. This week, maybe we go. in detail for the water integration. Water integration, then the following day is the gas integration. Mhm. This could be the last point. Yeah. Topics. The last. So the last step is the economic evaluation. So you need to understand that, yeah, although the design is thermodynamically perfect, but one way to test it is by calculating the payback period. If it's too long, then it's no good. So now that we have designed an incredible water network, we avoided crossing the pinch, map our cleansing first, minimize our utilities. On paper, the stream flow uh, beautiful. But now we have to present the design to the plant manager. So the first question, this is step five, economic evaluation. It's not about the cascading, water cascading, or the composite curve. It will be how much cost to drill. We need the capital capex. and how fast will they get their money back after the investment. So this is where the step five come in. So we translate the mass transfer and thermodynamic into the currency. To do this, we use the industry most trusted metric, one of the methods, payback period. So for payback period, the equation is simple. Net capital investment divided by net annual saving. So what is this term? So the net capital investment here refer to this upfront one-time cash needed to implement your pinch design. This include the cost of the new piping. Since in step four, we do the retrofitting, change the pipe flow direction, rerouting, the new pump needed, the valve, the control valve, the storage tank, critical for holding water in intermittent batch processes. Then the net annual saving or the OPEX saving, which is the denominator there. This is the cash the plant save every year. Remember the double penalty of water use. So every cubic meter of fresh water you save is a double win. Why? Because you save money on the purchasing the raw fresh water, and also you save money on the wastewater treatment that you wastewater treatment charges. Yeah, that's what I like. Okay. So no problem. Actually, problem eight. So the baseline no water use is 112.5 um, ton per hour of fresh water. So by doing the pinch network target, we recover the maximum water recovery is around 90 ton per hour. So the water safe is around 22.5 ton per hour. So assume that standard industrial utility parameter for this plant is 8,000. It operate 8,000 hours per year. Freshwater cost is around 2 ringgit per ton. The wastewater treatment cost is around 115, one, sorry, 1 ringgit 50 cent per ton. So the combined water utility cost is around 350 per ton. Freshwater and the wastewater. So the net annual saving, which is the 22.5 ton per hour, after we do the pinch network like this. So 22.5 ton per hour times 8,000 hour per year, the plant operating hour, times 3.50 per ton for the combined water utility cost. So we save around 630,000 ringgit per year. Yeah, that is how much you can save if you reduce the per percent. If you can reduce the freshwater use in this plant. So based on the process flow sheet, the plant needed 3 new piping line to route the decanter wastewater to the scrubber. The new transfer pump and the small intermediate water tank. So the estimated net capital cost is around 150,000, including the installation. So the payback period 150,000 divided by 330,000 per year. It's take around 8.5 months or 0.71 weeks, which is viable less than 8, 9 months. By reducing the amount of fresh water. Okay. Uh, I think that's all. So thank you for your attention. We resume back next week because like uh, different information, might be different book as well or source. Mm, okay.